lectures later on. Okay. I believe the recording has started now. So class, we are talking about interprocess communication, and specifically we will be talking about pipes and FIFOs. Now, what's the deal? IPC refers to the mechanisms that are made available to us by the operating system in order to be able to exchange data between processes. But not only that, IPC is more general than just communication, because it also involves solutions and tools that enable the synchronization of the actions of processes besides the communication. And it also includes as a package the signals.
So it is the creation of this file is wrong if you skip something.
Class, mute your microphones, please. We don't have to listen to you. You have to listen to me now. If you have any questions, please raise your hand. Here we have a small taxonomy of the mechanisms that are available in the IPC package. There are, of course, the signals. Now, we will not talk about the signals anymore. We will instead focus on the communication and synchronization parts. The communication module of the interprocess provided to our disposal, including pipes, FIFOs, sockets, message queues, shared memories, memory mappings, and so on. In synchronization, on the other hand, we have available different types of semaphores, file locks, mutexes, and condition variables. Now, each of these communication options for today, because we will only talk about communication today, not yet synchronization, they have different properties. Shared memory, for example, it simply allows multiple processes, 1, 2, 3, 4, 5, as many as you want, to communicate by simply writing and reading to and from a shared memory page. Mapped memory is very similar in principle to shared memory, with the difference being that it is associated with a file in the file system. So there is a certain file that is mapped into memory and not a direct allocation of a memory page. We will talk about this stuff in the upcoming weeks. This is just a very short introduction. Now, the pipes about which we will talk today, they allow sequential communication, so byte by byte, one after the other, from one process to a related process. So pipes can only be established between processes that have a parent-child relationship. FIFOs, on the other hand, are very similar to pipes. They have the same mechanism, the same operation mechanism, but they can be established between processes that are not necessarily related. Sockets are the most powerful communication mechanism that is available to us, and they can work not only between processes on the same machine, on the same system, on the same hardware, but they are the only option that is available for communicating between processes that are present on distinct systems. Sockets are the only option that is available for communication between processes on distinct systems. Now, how do you classify these IPC mechanisms? What are the criteria for their classification? Now, first of all, do they restrict communication to related processes or not? For example, pipes can only be used between related processes. Second, whether a communicating process is limited to only writing or only reading. So, given a certain mechanism, can you use it for bidirectional communication or unidirectional communication? 3, how many processes can use it in order to communicate? 2 or more than 2? And 4, whether the communicating processes are synchronized by the IPC. For example, if the reading process stops until data is available to read. I mean, is this done automatically, or do we have to take precautions in order to ensure this? So some IPC mechanisms have some synchronization tools available with them, but some others, they give you no synchronization support at all. So these are the criteria for classifying the different IPC mechanisms. Now, of course, we will not talk today about synchronization options, but since we are talking about IPC, the three main categories of synchronization tools that are available are, of course, the semaphores. We will talk about them in detail in the next week. File locks, and of course, mutexes and condition variables, which are specific to solving the synchronization issues of threads. So it is still early about these three topics. We will talk about them in the upcoming weeks. Now, IPC, of course, is not just an old and forgotten module of POSIX and Unix from many years ago. On the contrary, these mechanisms that we will talk about today and in the coming weeks, they form the basis, they form the fundamental basis of the state-of-the-art methods that are available today. For example, nowadays, we can easily make remote procedure calls using technologies such as, well, all technologies such as Java RMI or .NET Remote, more state-of-the-art. There are distributed object models, so objects that can be distributed across multiple systems, and so on. And all of them, if you look at their technical specifics, you will see that all of them are we'll be talking about the fundamental basis, the foundation of state-of-the-art methods that are available today. So let's say that today you are using .NET Remote or JSON RPC in order to make a remote procedure call. Now, what is a remote procedure call? Well, basically it is one system, one machine that executes a program that actually calls a procedure or function that is located on another machine. How can this be possible? Well, it is possible thanks to socket communication. But of course, in order to understand how RPC works, you need to be well fluent, you need to be knowledgeable on how socket communication works. And before sockets, we need to start from the beginning, and the beginning is pipes and FIFOs. Any questions, class? Any questions? No questions? Okay. Now let's talk about pipes, borular. Now this is the oldest available IPC method in the Unix and generally POSIX world. A pipe is a communication device that allows unidirectional communication. So if there is a pipe between two processes, this means one process can only send data with one pipe to the other process. So one process will be writing and the other process will be reading from that pipe. It doesn't go both ways. Pipes are serial devices, which means data will always be read at the other end of the pipe in the same order that it was written to the pipe. You can, of course, use it also in order to communicate between two threads, but in general, pipes are used for communication between processes. Now, of course, you have already used pipes indirectly. You have used them implicitly, dolaylı bir şekilde, when you used the symbol of the vertical bar on the shell, which actually creates a pipe. And what does it do? If, for instance, you type the command ls pipe wc, it takes the output of the ls command, it gives it to the pipe, as you can see at the bottom of the slide, and the output of the pipe becomes the input of the next command of wc. So basically it connects the standard output of ls to the standard input of wc, word count. And how does it achieve it? By simply using the pipe system call that we are going to study in detail in the upcoming slides. Of course, you could also obtain the same mechanism without using the vertical bar symbol, but instead by simply redirecting the output of the ls command to a file and setting the same file as input to the next command. This would have had the same effect. It would have led to the same result as using the pipe command. So the left part and the right part, same thing. It would have the same output, the same result. Now, what is a pipe? A pipe is simply a buffer that the kernel takes care of in kernel memory. You don't create the pipe. You don't create, sorry, the buffer. The buffer is created by the kernel. It is maintained by the kernel. This buffer, of course, is not infinite. It is finite, and of course, it has a limited capacity, which is usually about 64 kilobytes, depending on the system. So this means if a writer process writes faster than the reader process can read and consume the data, that means the buffer will be full, and that means the writer process, after the pipe is full, will be blocked. It will not be able to write anything else, anything further into the pipe. And what does it mean to be blocked? That means it will call the write or fprintf or whatever it uses in order to write to the pipe, and that system call will not return. That function will not return because it will be blocked. It will not be able to complete the writing statement. On the other hand, if the reader tries to read from the pipe, but there is no data available to read, similarly, it will also block until data becomes available. So in a way, indirectly, dolaylı bir şekilde, the pipe automatically synchronizes the pipe is full. So maybe it would overwrite the data and you will lose data. So fortunately, we do not have that problem because pipes are synchronized automatically. Any questions? So how do you set up a pipe between two processes? Now, of course, you use the pipe system call that you see right here. Now, the pipe system call receives an array of length 2, an integer array of length 2, and it returns 0 on success and -1 on error. For more details, you can check the man page. Now, what is the idea here? The idea is that you create an array of length 2 of integers, you pass it as an argument to the pipe system call. And what the pipe system call does is that it sets up the pipe in kernel memory. So it creates the buffer in kernel memory, and it places the reading file descriptor to the first position of this array and the writing file descriptor to the second position of this array. So file descriptor 0 in position 0 represents the reading end, and the file descriptor in position 1 represents the writing end of this pipe. Here, for instance, we have an example. We create an array of size 2, and then after we call the pipe system call, we get the reading file descriptor from position 0 and the writing file descriptor from position 1. And of course, you should always check for errors when you make system calls. So whatever you write now to the write fd, you will be able to read it from read fd. But of course, so far we only have one process, so it doesn't make any sense to have a pipe while you have a single process. So we should be creating at least one more child. Now, how can you use pipes in order to communicate between multiple processes? Now, the idea is the following. Let's say that the parent creates the pipe. Now, the parent process has created the pipe. So that means it has two file descriptors, one for the reading end and one for the writing end of the pipe. And then it calls fork, which means now we have two processes, the parent and the child. And the child process, of course, inherits the file descriptors of its parent, as we have talked about it when we were talking about files. The child process inherits the file descriptors of its parent. Now, the child also has access to the writing end and the reading end of the pipe. Now, if the parent process closes the reading end and the child process closes the writing end, well, in that case, you have a unidirectional communication mechanism. Whatever the parent process writes to the pipe, the child process will be able to read it from the pipe. Any questions? Okay. Here we have an example. Steps in creating a pipe to transfer data from a parent to a child. So we initially create an array of size 2, an integer array of size 2. We call the pipe system call. We check whether it has failed or not, of course. Then we call fork. So we create a child process. In case 0, so if the return value of fork is 0, so the process if the return value of fork is 0, that means we are in the child process. In that case, we close the writing end of the pipe, but the reading end is still open. Then we break away from the switch cause. And in the default case, so if fork returns something other than -1 and 0, that means we are the parent process. The parent process closes the reading end, and it breaks away from the switch case close. Another example, using a pipe to communicate with a child process. Now here we have two functions, the writer and the reader. Let's look at the main function first. We will get back. Now in the main function, we create an array of an integer array of size 2. We call pipe. We should be checking for the return value, of course, too. Then we call fork. And if the return value of fork is 0, that means we are in the child process. What does the child process do? It closes the writing end, and then it converts the reading file descriptor to a stream variable type. So from an integer file descriptor to a file pointer by using fd open. And then it gives that file pointer to the reader function. And what does the reader function do? The reader function gets that file pointer. It the pipe by using fgets. Efendim? Yes?
Özür dilerim hocam, sesiniz kesildi de az önce. Bir 4-5 saniyelik sesiniz kesildi. O sırada anlattıklarınız gelmedi.
Okay, thank you for letting me know. Now, we are in the reader function. The reader function is executed by the child process. The child process has converted the reading end of the pipe into a file pointer. The reader function first declares a buffer of size 1 kilobyte. And while it hasn't reached the end of the stream, so as long as it doesn't encounter an end of file character, it keeps on reading from the pipe by using fgets. It tries to read 1 kilobyte and it places it into the buffer. And then it simply prints the contents of the buffer to standard output. And what about the parent process? The parent process here in the else clause at the bottom of the slide, it closes the reading end, it converts the file descriptor into a file pointer, and it gives the file pointer to the writer function along with a simple string, hello world, and an integer 5. The objective is to write 5 times hello world into the stream. Let's look at the writer function. The writer function Class, can you hear me?
Yes.
Class, can you hear me?
Yes, sir.
We are having some network issues today, I think, in the campus. I just talked to the other faculty members, and they said that they are also having some problems. So hopefully the stuff will be resolved. But in the meantime, we have to continue. Now, I was talking about the parent process. The parent process, which is executing the writer function. And the objective of the writer function is to count times the message to the file pointer stream. And that's exactly what it does. In a simple for loop, it repeats, that is repeated count times. It fprintfs the message to the stream, and it sleeps 1 second between each printing. Now, what does fflush do? Do you remember it? Here we have an fflush after fprintf. What is the objective of fflush?
It is directly printing.
is directly printing. Can you elaborate? I mean, if printf also prints.
Buffer. Don't wait the full of buffer. It's directly.
It flushes the buffer. Class, can you hear me now?
Yes.
Class, I mean, we are having some significant network issues, so I'm going to stop at this point because this is getting a bit too difficult under these conditions, both for you and for me. And I suggest we continue at 1:30. Okay. Okay. Some of you cannot even hear me, so I will write it to the chat box. So class, I wrote it to the chat box. For those of you who can hear me, we are stopping now, and I will continue the lecture from my place at 1:30 during the second session. Because this, well, it cannot continue like this right now. So I'll talk to you at 1:30. Take care.
Have a nice day, sir.
Thank you.
To class. Bye.